Acid-base equilibrium. Acid-base properties of salt solutions. In this tutorial, we will be going over salt solutions that contain anions of strong acids, anions of weak acids, cations of weak bases, cations of strong bases, and finally cations with small atomic radii and high positive charges. Acid-base properties of salt solutions. Let's look at some properties of chemical salt solutions. We need to understand that ions can exhibit acidic or basic properties. Many ions are able to react with water to generate hydrogen ions or hydroxide ions. We also need to consider the ions of which the salt is composed. So some assumptions about chemical salts. Nearly all salts are strong electrolytes. In other words, they're able to conduct electricity. And nearly all salts dissolve completely in water. To be sure about that, we need to look at KSP values. Anions of strong acids. An anion that is the conjugate base of a strong acid will not affect the pH of the solution. So for example, hydrochloric acid reacting with water will form hydronium ions and the chloride ion. HCl is a strong acid. Therefore, the chloride ions will have a negligible tendency to abstract or pull protons from water and will not influence the pH of the resulting solution. Another way of thinking about this is that the chloride ions does not result in the production of hydroxide ions, so the pH will not decrease. Cl-1 is always a spectator ion in acid-base chemistry. Let's look at another example. We have nitric acid reacting with water to form hydronium ions and the nitrate ion. The nitrate ion, NO3-1, produced will not affect the pH of the aqueous solution. This anion will not abstract or remove hydrogen ions from water and therefore will not increase hydroxide ion concentration in the solution. Anions of weak acids. An anion that is the conjugate base of a weak acid will cause an increase in pH. In other words, the solution will become more basic. So for example, HPO4-2 reacting with water produces H2PO4-1 and hydroxide ions. In this situation, HPO4-2 accepts a proton from water and is identified as a weak base, as we can see right here. So the water is going to donate a hydrogen ion to the HPO4-2. H2PO4-1 is a weak acid and hydroxide ions are produced. If we think about conjugate acid-base pairs here, the HPO4-2 and the H2PO4-1 is a conjugate acid-base pair, and the water and the hydroxide are conjugate acid-base pairs. As a result, the pH will increase and the solution will become more basic. Let's look at another example. Here we have the carbonate ion, CO3-2, reacting with water to form the hydrogen carbonate ion and hydroxide ions. Water is donating a proton to the carbonate ion. As a result, we form the hydrogen carbonate ion and hydroxide ions. As soon as we see this hydroxide ion right here, we know that the pH is going to increase and the solution is going to become more basic. Cations of weak bases. A cation, or a positive ion, that is the conjugate acid of a weak base will cause a decrease in pH. In other words, the solution will become more acidic. Let's look at this example. We have the ammonium ion reacting with water to form ammonia and the hydronium ion. NH4+1 donates a proton to water and is identified as a weak acid, as we can see right here. Hydronium ions are produced and the pH decreases. So again, when we look at this reaction, we can see our conjugate acid-base pairs. And as soon as we see that the hydronium ion is produced, the pH will decrease and the solution will become more acidic. Let's look at another example. We have C5H4NH+1 reacting with H2O produces C5H4N and the hydronium ion. The C5H4NH plus 1 is acting as a weak acid. It's going to donate this labile proton right here to the water, which is acting as a weak base. We form the conjugate base C5H4N and the hydronium ion. So once more, as soon as we see the hydronium ion formed, the pH will decrease and the solution will become more acidic. Cations of strong Arrhenius bases. The cations of group 1A and heavier members of group 2A will not affect the pH of a solution. So we have two examples here. We have sodium hydroxide reacting with water to form sodium ions, hydroxide ions, and hydrogen gas. We also have strontium hydroxide reacting with water to form strontium ions, hydroxide ions, and again, hydrogen gas. NaOH and SrOH2 are strong bases. The Na plus 1 and Sr plus 2 cations are spectator ions and will not influence the pH of the solution. Metal cations that have a small ionic radius and a higher positive ion charge. Metal cations, which have a small, higher positive charge, form weakly acidic solutions. So two examples are the aluminum ion and iron plus 3 ions. Reaction 1. Al plus 3 reacts with H2O to form Al H2O6 plus 3. This is an example of coordination chemistry, where a heavy metal is hydrated by surrounding the ion with water molecules. The hydrated form of the ion, Al H2O6 plus 3, acts as a Bronsted-Lowry acid. Here's another reaction. Al H2O6 plus 3 reacting with water forms Al H2O5 OH plus 2 and the hydronium ion. Neither the alkali metal cation nor the alkaline earth metal cations ionize in water in this way. So in other words, your group 1 and your group 2 metals. Many other metals do undergo this process in water. The smaller and more highly charged the cation, the more acidic the behavior. Let's do some practice. Classify each cation as a weak acid or pH neutral. Cr plus 3 is a transition metal with a high positive charge. Therefore, it will be classified as a weak acid. Cs plus 1 is a group 1 metal with a low charge, so that will be classified as neutral. Fe plus 2 is a transition metal with a plus 2 charge. That would be classified as a weak acid. Final thought. When a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the ion with the larger equilibrium constant, Ka or Kb, will have the greater influence on pH. So that's something that we need to pay attention to. So what did you learn? We talked about salt solutions that contain anions of weak acids, cations of weak bases, cations of strong bases, and cations with small atomic radii and higher positive charges. Need more help? Feel free to contact me. Have a great day.